I'm Deja Cipher, and I'm going to review an alternative approach to a power analysis, an a priori power analysis for an exploratory or pilot study. On this channel is already a review of chapters 24 and 25 in the Grove and Cipher textbook that reviews traditional power analyses, effect sizes, and how to put together a power analysis using G-Power. This presentation focuses on what researchers may choose to do if they have a pilot or exploratory study. So let's review. In a traditional a priori power analysis, you would specify your research questions, decide which statistics that you're going to need to compute to address each part of the questions, identify the primary research question if you have more than one. If you have multiple primary research questions and not a primary and a secondary, if you have multiple primary, you will want to perform a power analysis for each primary research question. You'll identify anticipated effect sizes from the existing literature or from your own pilot data, which is the hardest part of a power analysis because you have to scour the literature, search in all of the corners of the literature to find an apples to apples kind of effect size to use in your power analysis. That is a challenge. Identify your study alpha, study beta. Of course, 1 minus beta is the statistical power. And then perform the power analysis to identify what your required sample size is based on your effect size, your alpha, and your beta. Now, for an exploratory situation, what you have is a situation where you are not able to find any kind of apples to apples effect size in the literature. You are planning a study that has absolutely never been investigated before. Your research question is unique. Your research question is novel. So we have issues with that, right? That means you don't have a value. You don't have an effect size value, an effect that you can enter into that power analysis for a valid result. It can be so difficult to perform a pilot study to obtain those effect sizes if you don't have the resources or the time to do that. One option is to communicate with experts in that existing field to obtain information about any possible unpublished findings, unpublished data, where you might be able to work with that expert to extract an effect size from their data. Some researchers alternatively will just say that they will use a conservative effect size, meaning a very small effect in the power analysis, which, as we've learned from reviewing in the other presentation, using a very small effect size in a power analysis is going to yield a very large required sample size. So there are obviously lots of disadvantages to that if the researcher doesn't have the resources to enroll that many participants, if the researcher doesn't have the time to do that. And also, and perhaps most importantly, if the research carries with it some level of risk, then doing a power analysis that intentionally yields a possibly falsely high number of required participants and putting those participants at risk may be considered unethical. On the other hand, if a researcher guesses and uses a very large anticipated effect in their power analysis, that will generate, of course, the least amount of required participants, but that would also be a false power analysis because, again, they're guessing. So the risks with that is they'll conduct the study, they will have generate data that are underpowered and therefore be at risk for type 2 error, meaning that their results may be not significant, and that non-significance is either due to no actual effects in the data or that there are effects, but the data or the sample size is not large enough to test the effect. So an alternative to power analysis for a pilot or exploratory study to address these problems would be to determine a fixed sample size number that would be feasible and reasonable with the resources that the researcher has and within the timeline that the researcher is working with. The researcher can build a table of effect sizes that is a range of effect sizes to where each possible effect generated is associated with a certain level of statistical power based on that selected fixed sample size. And what that does for you is it provides a range of possibilities without locking in on one value by guessing, either over or underestimating some effect size. You have a range of possibilities because the researcher just doesn't know. Now, here are some ranges of types of effects that are reviewed in the Grove and Cipher workbook. These are the 7 most common effect sizes. And I divided the table into what's considered a small, a moderate, and a large effect. You have the Cohen's d, comparisons between 2 groups on a continuous dependent variable. Cohen's dz for paired samples. Cohen's f, comparing more than 2 groups. The Pearson R correlation, the R squared for linear regression, OR, the odds ratio, and D, which is short for difference between 2 proportions. Here is an example of how we might write a power analysis section for a pilot or exploratory study. So we're listing the software used to perform the power analysis. We're listing the type of analysis anticipated. Here is an example using mixed factorial analysis of covariance. And we're listing the alpha of 0.05. And we're listing the fixed sample size of 60 participants. So in this hypothetical example, the researcher can feasibly enroll 60 participants with their limited resources and timeline. And therefore, a table was generated using G-Power that presents a range of potential effect sizes based on that fixed sample size of 60. Let's take a look at the table. So this is what a table might look like for using the effect size, the Cohen's F effect. And then, so you have a range of 6 possible effect sizes ranging from small, 0.15, to large, 0.40, and everything in between. You can choose to report ranges by 0.05 or 0.1. It's a call by the researcher. And then under that, you can see the associated statistical power for each and every effect size in this table. So as you can see at Cohen's F of 0.3, which is a moderate effect size, according to our table, 0.3 actually reaches statistical power, our goal of 0.80, which is pretty much a gold standard for desired level of power. Anything at 0.8 or higher, that is our power goal. So you can see this last sentence, although exploratory studies are commonly underpowered, adequate power will be achieved if the difference is greater than an F of 0.30, a moderate effect. That is how that might be presented in this type of, with this type of study. Here's another example using a Pearson R correlation coefficient. So we have this hypothetical example. We are planning to enroll 100 participants we are planning for Pearson correlations to be our statistical analysis at a two-sided alpha of 0.05, beta of 0.2, meaning that our power goal is 0.8. And so let's take a look at the table here. So you have 5 presented effect sizes from 0.1, which is a small Pearson R, all the way to 0.5, which is considered a large Pearson R. And you can see the associated statistical power for each and every Pearson R value. And you can see at a Pearson R value of 0.4 that statistical power far exceeds our goal when you have a sample size of 100. In fact, even a moderate R of 0.30 will exceed the power requirement of 0.80. If you noticed at this at the very bottom of this example, adequate power will be achieved if our study correlations are at R of 0.28 or higher. How did I do that? Well, I'll show you how to do this in G-Power. I have G-Power open to perform the power analysis for a Pearson R here. You can see my test family, all of my menu systems set up. Now, one thing we do need to change and what's different from a traditional a priori power analysis, this alternative is going to have to use a different menu system. Instead of a priori in the type of power analysis menu, we are going to need to pull down and choose the post hoc choice here, because we're going to have a fixed N of 100, two-tailed, okay? And we're not technically performing a post hoc power analysis. This is still an a priori power analysis because we're performing this power analysis before the study begins. Rather, we need to use this particular menu to achieve our goals and build this table. So how you would build this table is you would enter multiple effect sizes. So we would start with 0.1, alpha of 0.05, are fixed in. This last entry is that our null hypothesis is that our correlation will be 0. So when you click on calculate, you can see that the power yield for an anticipated effect size of 0.1 is 0.167 rounded to 0.17 here. And then you keep going for 0.2, for 0.3, 4, and 5. And that's how you build your table. Now, before the last sentence of my power analysis summary stated that if the actual R value after we analyze our data is greater than 0.28, then desired power would be achieved. How would one do that? Well, you have to go back and forth. It's iterative. So you can see at a correlation of 0.3, the desired power is exceeded. But if you enter 0.27, the desired power would not be achieved. It's just below at 0.782. At 0.28, it does meet our desired power of 0.80. So it's somewhere between 0.27 and 0.28, but because APA requires numerical values to be reported only at 2 decimal places, then we would just enter 0.28 as our target Pearson R to achieve desired statistical power. So that's how you might present an alternative a priori power analysis for a pilot or exploratory study. Hope this helps.